We now have a model for our linearly separable support vector machine, or SVM, which is, it's linear, it's a line, and we have parameterized what we want this model to do, which is to always have the product of the class label y times that dot product of w and x, w of course being the model, x being the data, plus b, also part of the model, being greater than or equal to 1. But now what we have to do is get back to that margin, right? Because we've got to figure out what is that orientation and offset of the line in order to maximize something. And what we said with the SVMs is that we're going to maximize this margin. What is the margin? We're going to take the data point in one class that is closest to a separating line and a data point on the other, and make sure that it is maximally distant so that we have a clean separation. All right, so let's see how to actually do that now. All right, let's take a point x1 in the red class and put it on this line. And let's consider the corresponding blue point over here. Now, what is w? W is that little vector that is perpendicular to the separating surface. Okay? So if x1 is this, let's think about what happens when we move up to the other side of the classification surface. Well, x2 is just x1 plus lambda, some scale factor, times that little vector w. I've just taken x1, and what am I going to do? I'm going to push it along perpendicular to the line until I get to the other side of the classification boundary. And so x2, its corresponding point here, is just this point plus lambda w, of course w being the normal vector to the line. Okay, good. Well, what do we want to do? We want to maximize that difference, right? We want these points, we want to separate those blue and the red points as much as possible. So we want to maximize lambda times the vector norm of w. Maximize the gap that we have in here. All right, well, okay, now we have an objective. We want to maximize something. How? Well, the first question is, well, what is lambda? I know what w is the model parameter, but where do I get lambda from? Well, let's derive that. All right, so same picture. I've got my x1, class 1. I've got my w, which is the vector that is perpendicular to the line. And the corresponding point x2 here is x1 plus lambda w. All right, now what do we know about points that lie on the line where now the intercept is down below? It's not at 0. It's that w, x2 plus b must equal to 1. Why 1? Because this is lifted up above the origin at a unit value here. So remember that for the dotted line that goes to the origin, everything that above is, the dot product of everything above is positive, the dot product of everything below is negative, and of course if it's on this line right here, then w x2 plus b is equal to 1. All right, what is x2? Well, x2 is related to x1 because it is just x1 plus lambda w. So let's go ahead and substitute that in here. So now I've got w times x1 plus lambda w plus b is equal to 1. All right, let's do a little bit of algebra. W times x1, I'm going to bring the b over here because I want to isolate the lambda, plus lambda w transpose times w is equal to 1. All right, let's see. What is w transpose x plus b? Well, that is this thing, this little guy right here, and that's equal to -1 because that's down below. And so now I can rewrite this as -1 is equal to lambda w transpose w, which is equal to 1, which tells me that lambda is equal to 2 over the dot product of w with itself, w transpose w. Interesting. Now I have an answer to what lambda is for this margin. All right. So now what do I want to do? Well, let me rewrite this. Lambda is equal to w transpose w. Remember what that is? I take a vector, I take a dot product with itself, I sum the square, so that's just the vector norm squared. Okay, so lambda is 2 over the vector norm squared, which sort of looks a lot like that over there. Now, what are we trying to do? We're trying to maximize this quantity here, lambda times the norm of w. Well, if lambda is this here, then what I want to maximize is the margin, which is, of course, just simply 2 over the vector norm w. This vector norm squared and this vector norm, one of them cancels, and I'm left with 2 over the vector norm, which is just, of course, the 2 over the square root of W transpose W. And that is, now I have something I want to maximize. I want to maximize that gap, and I have it written out, so I want to maximize 2 over the vector norm of W. Good. Now, I can't just do that. If I was just doing that, I would just drive W to infinity. I have other constraints, which is I want all the blue on one side and all the red on the other side. We're going to bring that back in a second. So now what I want to do is do 2 things. I'm going to frame this as a minimization problem. So instead of maximizing 2 over omega, I'm going to minimize the inverse of that, and I'm going to knock off the square root because it's going to make the minimization easier, and I don't care about a square root because it doesn't change the minimization. It's just a compressive nonlinearity. So I'm going to find the W and the B, right? Remember, the model is the vector and the offset that minimizes W transpose W over 2, which is the same as maximizing the margin. Here it is, subject to the constraint that we have correct classification. So that is that the label y times W times x plus b, there are my unknowns, should always be greater than 1. When this is negative, this should be negative. When this is positive, this should be positive for all I. And so now look at what we have. We have a constrained optimization. This is what we want to optimize. Minimize W transpose W over 2. Obviously, if that's all there was, I would just drive W to 0, which would be the same as maximizing the margin because I would make it infinitely far away. But it has to be subjected to this. Now, how do we do this optimization? The reason why this is such a nice formulation is it falls under the category of quadratic programming. We are not going to talk about the details of quadratic programming, and that belongs in an optimization class. I will show you how to do this with, in Python with the SVM libraries, but what you should know is that there are very nice optimization techniques that will solve this using quadratic programming that will maximize the margin, minimize this quantity, subject to this constraint that we have perfectly separated data. Okay. So if you want to know how quadratic programming works, I encourage you to go look up an optimization book or an optimization class. What we're going to do next is I'm going to show you how to implement this, and then we're going to go from linearly separable SVMs to non-separable linear SVMs to nonlinear SVMs. We'll be back in a few minutes.